Induced ground current, or IG, refers to electrical current that flows through the ground where a time-varying magnetic field is present. This magnetic field can be generated by natural phenomena such as lightning strikes, or by human activities such as the operation of high-voltage power lines and alternating current electrical systems. The effects of induced ground current can vary depending on its intensity and duration. Firstly, electromagnetic interference, or EMI, can occur. Induced ground current can interfere with electronic devices, causing malfunctions or data corruption. Secondly, corrosion of underground structures can be accelerated. Induced ground current can accelerate corrosion of metal structures, such as pipelines and cables buried in the ground. Thirdly, safety hazards can arise. Induced ground current can create a shock hazard for people in contact with the ground or metal objects connected to the earth. Several methods can be employed to mitigate induced ground current. One is shielding, using conductive materials to surround or shield sensitive electronic devices and underground structures. Another is grounding, providing a low resistance path for induced ground current to flow through, reducing the potential difference between the ground and metal objects. Isolation involves separating susceptible equipment and structures from induced ground current sources. Finally, magnetic field reduction aims at reducing the magnetic field intensity at the source, such as by using underground power lines. Research on induced ground current is ongoing, focusing on improving mitigation techniques and understanding its long-term effects. Applications of induced ground current include geophysics, using induced ground current to study the electrical properties of the Earth's subsurface. Another application is lightning protection, designing lightning protection systems to minimize induced ground current effects on structures and equipment. Lastly, safety in electrical substations involves protecting workers from induced ground current hazards in high-voltage environments. The Institute of Electrical and Electronics Engineers, or IE, has a working group on induced ground currents. The National Lightning Safety Institute, or NLSI, provides guides to induced ground current. IE's Standard 1410.2017 is a guide for the measurement of power frequency ground current parameters. Induced ground current is a complex phenomenon with significant implications for electrical systems and safety. Understanding its causes, effects, and mitigation techniques is crucial for engineers, technicians, and anyone working with or near electrical infrastructure. The time-varying magnetic fields that induce these currents can originate from various sources, both natural and man-made. Natural sources include geomagnetic disturbances caused by solar activity, which can induce ground currents over large areas. Man-made sources are more localized and include power transmission lines, electrical substations, and industrial equipment. The magnitude of the induced ground current depends on several factors, including the strength of the magnetic field, the conductivity of the soil, and the geometry of the grounding system. High-voltage power lines are a significant source of induced ground currents. The alternating current flowing through these lines creates a magnetic field that induces currents in the surrounding earth. These currents can then flow through buried metal structures, such as pipelines and cables, causing corrosion and potentially leading to failures. Electrical substations, with their high concentration of electrical equipment, are also a major source of induced ground currents. The transformers, switchgear, and other equipment in a substation generate significant magnetic fields that can induce currents in the ground. These currents can pose a safety hazard to workers and can also interfere with the operation of sensitive electronic equipment. Industrial equipment, such as welding machines and induction heaters, can also generate significant induced ground currents. These currents can be particularly problematic in industrial environments where there are many interconnected metal structures. The effects of induced ground current can be wide-ranging and can impact various systems and equipment. One of the most common effects is electromagnetic interference, or EMI. Induced ground currents can create noise in electronic circuits, which can lead to malfunctions, data corruption, and communication failures. This is particularly problematic for sensitive electronic equipment such as computers, communication systems, and medical devices. Corrosion is another significant effect of induced ground current. When induced ground currents flow through buried metal structures, they can accelerate the corrosion process. This can lead to premature failure of pipelines, cables, and other underground infrastructure, resulting in costly repairs and potential safety hazards. Safety hazards are also a concern. Induced ground currents can create a shock hazard for people who come into contact with the ground or metal objects connected to the earth. This is particularly dangerous in areas where there is a high concentration of electrical equipment, such as substations and industrial facilities. To mitigate the effects of induced ground current, various techniques can be employed. Shielding involves using conductive materials to block or divert the magnetic fields that induce the currents. This can be achieved by surrounding sensitive equipment with a grounded metal enclosure or by burying conductive mesh in the ground. Grounding is another important mitigation technique. By providing a low resistance path for the induced ground currents to flow, the potential difference between the ground and metal objects can be reduced, minimizing the risk of shock hazards and corrosion. This can be achieved by installing a comprehensive grounding system that connects all metal structures to a common ground point. Isolation involves separating susceptible equipment and structures from the sources of induced ground currents. This can be achieved by using insulating materials to isolate equipment from the ground or by relocating equipment away from high magnetic field areas. Magnetic field reduction involves reducing the intensity of the magnetic fields that generate the induced ground currents. This can be achieved by using underground power lines, which produce lower magnetic fields than overhead lines, or by optimizing the layout of electrical equipment to minimize magnetic field emissions. Research on induced ground current is ongoing, with a focus on developing more effective mitigation techniques and understanding the long-term effects of these currents. One area of research is the development of new materials and methods for shielding and grounding. Another area of research is the development of computer models that can accurately predict the flow of induced ground currents in complex environments. The applications of induced ground current research are diverse and include geophysics, lightning protection, and safety in electrical substations. In geophysics, induced ground currents are used to study the electrical properties of the Earth's subsurface. By injecting currents into the ground and measuring the resulting magnetic fields, geophysicists can create detailed maps of the subsurface geology. This information can be used to explore for mineral deposits, assess groundwater resources, and monitor environmental pollution. In lightning protection, induced ground currents are a major concern. Lightning strikes can generate very high currents that flow through the ground, potentially damaging equipment and posing a safety hazard. By understanding how induced ground currents behave during lightning strikes, engineers can design more effective lightning protection systems. In electrical substations, induced ground currents can pose a significant safety hazard to workers. By implementing appropriate mitigation techniques such as grounding and shielding, the risk of shock hazards can be minimized. The IEE Working Group on Induced Ground Currents is a valuable resource for engineers and technicians working in this field. The working group develops standards and guidelines for the measurement, analysis, and mitigation of induced ground currents. The NLSI also provides valuable information on induced ground currents, including guides and training materials. IEE Standard 1410.2017 provides guidance on the measurement of power frequency ground current parameters. This standard is essential for anyone involved in the design, installation, or maintenance of electrical systems. Understanding and mitigating induced ground current is crucial for ensuring the safety and reliability of electrical systems and infrastructure. By implementing appropriate mitigation techniques and staying informed about the latest research, engineers and technicians can minimize the risks associated with induced ground currents. Furthermore, a deeper dive into each mitigation technique reveals nuanced strategies and best practices. For instance, effective shielding involves not only selecting the right conductive material but also ensuring proper grounding of the shield to prevent the buildup of charge. The choice of material depends on the frequency of the magnetic field being shielded, with higher frequencies requiring materials with better conductivity. Similarly, grounding systems must be carefully designed to provide a low impedance path for ground currents. This includes selecting the appropriate grounding conductors, ensuring proper bonding of all metal structures and minimizing ground loops. The design of a grounding system should also consider the soil resistivity, which can vary significantly depending on the location. Isolation techniques can range from simple measures, such as using rubber mats to insulate workers from the ground, to more complex solutions, such as using fiber optic cables to isolate communication equipment from electrical noise. The key is to identify potential pathways for induced ground currents and break those pathways with insulating materials. Magnetic field reduction can be achieved through various methods, including optimizing the layout of electrical equipment to minimize magnetic field emissions. This involves careful placement of transformers, switchgear, and other equipment to reduce the overall magnetic field in the area. Another approach is to use magnetic shielding materials to contain the magnetic fields generated by electrical equipment. These materials can be applied as coatings or incorporated into the design of equipment enclosures. In addition to these mitigation techniques, regular monitoring and testing of grounding systems is essential to ensure their effectiveness. This includes measuring ground resistance, checking for loose connections, and inspecting for corrosion. Any issues identified during monitoring and testing should be promptly addressed to maintain the integrity of the grounding system. Furthermore, education and training are crucial for ensuring that workers are aware of the hazards associated with induced ground currents and how to protect themselves. This includes training on proper grounding procedures, safe work practices, and the use of personal protective equipment. By implementing a comprehensive approach to induced ground current mitigation, organizations can minimize the risks associated with these currents and ensure the safety and reliability of their electrical systems and infrastructure. It is also important to consider the regulatory requirements and industry standards that govern the design, installation, and maintenance of electrical systems. These requirements and standards are designed to protect workers and the public from the hazards of electricity, including induced ground currents. Adherence to these requirements and standards is essential for ensuring compliance and minimizing liability. The long-term effects of induced ground currents are an area of ongoing research. While the immediate effects of these currents, such as EMI and shock hazards, are well understood, the long-term effects on underground infrastructure and the environment are still being investigated. Some studies have suggested that induced ground currents could contribute to the degradation of underground pipelines and cables, leading to premature failure and environmental contamination. Other studies have explored the potential effects of induced ground currents on plant growth and animal behavior. More research is needed to fully understand the long-term effects of induced ground currents and to develop strategies for mitigating these effects. In addition to the technical aspects of induced ground current mitigation, it is also important to consider the economic and social implications. The costs associated with induced ground current damage can be significant, including the costs of repairs, replacements, and lost productivity. In some cases, induced ground currents can also lead to environmental damage, resulting in additional costs for remediation and cleanup. By investing in effective mitigation techniques, organizations can reduce the long-term costs associated with induced ground currents and protect their assets and the environment. Furthermore, the social implications of induced ground currents should not be overlooked. Power outages, equipment failures, and safety hazards can all have a negative impact on communities and individuals. By ensuring the reliability and safety of electrical systems, organizations can contribute to the well-being of society. Induced ground currents are a complex and multifaceted issue that requires a comprehensive and integrated approach. By understanding the causes, effects, and mitigation techniques associated with these currents, organizations can protect their assets, ensure the safety of their workers and the public, and contribute to the long-term sustainability of their operations. This includes embracing new technologies and approaches for monitoring, analyzing, and mitigating induced ground currents, such as the use of advanced sensors, data analytics, and artificial intelligence. By staying at the forefront of innovation, organizations can ensure that they are well prepared to address the challenges posed by induced ground currents in the future. The complexity of induced ground current phenomena necessitates continuous learning and adaptation. As new technologies emerge and our understanding of these currents evolves, it is crucial to remain informed and adjust mitigation strategies accordingly. This includes actively participating in industry forums, attending conferences and workshops, and engaging with researchers and experts in the field. By fostering a culture of continuous learning and improvement, organizations can enhance their ability to manage the risks associated with induced ground currents and maintain the reliability and safety of their electrical systems and infrastructure. In conclusion, induced ground currents are a significant concern for electrical systems and infrastructure. Understanding their causes, effects, and mitigation techniques is essential for ensuring safety, reliability, and long-term sustainability. By implementing a comprehensive and integrated approach, organizations can effectively manage the risks associated with induced ground currents and contribute to a safer and more sustainable future. This requires a commitment to continuous learning, innovation, and collaboration, as well as a willingness to adapt to new challenges and opportunities.